Hello everyone, so this is our lecture 22 of our subject digital system design, and today's topic is bidirectional shift register and universal shift registers. So these are the contents of today's lecture. First we will be covering the concept of the bidirectional shift register, and then we will proceed towards the circuit of the bidirectional shift register, and then we will discuss the concept of universal shift register, what all tasks can be done using universal shift register, and then converting that concept into a circuit. Okay, so let's start with the concept of bidirectional shift register. So bidirectional shift register is the basically SISO shift register only, serial in serial out shift register, which we have covered in our last lecture. In that there is a single input terminal which can accept the input, and there is a single output terminal through which the data can exit the shift register. Okay, so in bidirectional shift registers there are basically two provisions. That means data can be shifted from left to right, okay, or from right to left. So these are the two possibilities in which data can be shifted in a bidirectional shift register, but the main concept is of the SIS only. So let's understand that concept first, how we are going to implement this. This is not the actual circuit, but we are discussing the concept how the data will be flowing from left to right and right to left. So if data is being fed from the left side, okay, so D-inf is from left side, so it must exit from the right side, so this must be the path. Okay, so this can be D out from right side. So this can be the path for left to right shift, which is the simplest one, which we have already covered in the previous lecture of the basic SISO shift register. Then coming to the second mode, right to left, that means data has to be from the right side. So for this, let's change the color. Now the data will be from here. This will be the data in from right side, okay, and this data enters from here, exits from here, enters the input of the next flip flop, exits from here, enters the input of next flip flop, exits from its output, and then enters from this one, and this will be the final D out. Okay, D out from left side. So this is something which we want to implement in a single circuit. But like as in the case of PISO shift register, there are two possibilities. At any point of time I have to choose between these two inputs, either this one or this one. Okay, so both the things cannot be done simultaneously, neither we are interested in performing both the things simultaneously, because in a single application either we will be shifting from left to right or right to left, but there has to be some controlling mechanism by which this left and right shifting can be controlled. Okay, so there has to be something between the flip flops which will control the selection of these inputs to the next flip flops input. Okay, so that means either this DB is going to accept QC, or this is actually DC, this is QC. Okay, so at this terminal either the output of the left flip flop will be arriving or the output of the right flip flop will be arriving. Okay, so with that angle in mind, now let's proceed towards the actual circuit of the bidirectional shift register. Okay, and this is the basic thing which we have already covered in the previous lecture of the shift registers. That means an n bit shift register uses n flip flops and can store n bits. Okay, so now let's proceed towards the circuit. That means there has to be something in between the flip flops, and that something will definitely be a multiplexer. A 2x1 multiplexer can solve the issue by choosing appropriately between the two inputs. The two inputs of the multiplexer will be the outputs of the left and the right flip-flop. Okay, and the select line will decide which output, left one or right one, will be connected to the next flip-flop's input. Okay, so that's why we will be connecting the multiplexers between the flip-flops. So let's proceed towards the actual circuit. Okay, so let's proceed towards the circuit in which we are having a 2x1 multiplexer, which is having two inputs and one output. Similarly here as well, two inputs and one output. Another 2x1, two inputs and one output. Another 2x1 multiplexer, two inputs and one output. Okay, so now let's start preparing the connections. One connection has already been made, that is the clock connection for all the flip-flop is connected to a common point, because shift register, as we have discussed in our previous lecture, the shift registers are synchronous circuits, so that's why the clock is common to all the flip-flops. So there are four multiplexers. Now let's prepare the circuit. This thing, okay, will be my D in. Okay, D in from left side. So this is my D in from left side, and it can enter this flip-flop. Output of this will be connected to the input of the next multiplexer, and its output will be connected to the next flip-flop's input. Similarly here as well. And here as well. So this completes the path for left to right shift. The only thing which we need to do is to choose the select line. So select line can be made common to all the flip-flops. So let's denote the select line with the black color. So this select line is common to all the flip-flops. So this mode, whether we want to perform left to right shifting or right to left shifting, it can be named as mode. If mode is equal to 0, okay, then we are shifting from left to right, and if mode is 1, then we will be shifting from right to left. Okay, so we have to appropriately name these inputs as well: 0 1, 0 1, 0 1, 0 and 1. This is my Y terminal output, single output of the multiplexer. So it is very much clear, if I choose this as 0, then all the 0 inputs of the multiplexer will be selected, and the path for the left to right shifting will be established. Now if I want to perform right to left shifting, okay, so for this we have to prepare a separate isolated path. Okay, so from that onward we have to prepare a separate path. So in that case, this will be my D in, but this D in will be from the right side. Okay, this D in is for the right side. With this I have to choose mode is equal to 1, and after doing this, the output of this QD will be connected to the input of the left one. Okay, that means this will be the connection. Similarly, this QC output will be connected to the DB input. Similarly here, okay, and the output of this QC will be my final D out, and this D out is from the left side. So similarly we can mark the D out for right side as well. Okay. So in this way we can see that both left and right shift paths can be established using the same circuit by appropriately controlling this mode input. So this mode input will decide whether I will be performing left shifting or right shifting. Okay. And this left shifting and right shifting is very much important in communication systems, where we have to perform multiplication and division. As you can see that if I am having a data like this one, if this is the data and this corresponds to, you can see that this is equivalent to your 8. Okay. So if there is one left to right shift, that means it will become 0 0 1 0 0, that means it becomes 4. Okay. And if there is a left shift, then it will become 1 0 0, 1 4 times 0. In that case it will become 16. So we can see that if we are shifting towards the left, then we are multiplying by 2. Okay. And if we are shifting towards right, we are dividing by 2. So we can divide the number by 2 or multiply the number by 2 by simply shifting it towards the left or right. Okay. So this is where this left and right shifting is practically used. Okay. So now let's come to the concept of the superior most shift register, which is named as universal shift register. So universal shift register, as the name suggests, that a single shift register circuit will be capable of performing all the shift register operations which we have covered so far. So we have covered SISO, SIPO, PIPO, PISO, and this bidirectional. Okay. Bidirectional, this also we know, we have already covered. SISO with left to right and right to left shift. Okay. So this all we have to cover in a single circuit. Now you can, but the thing is, we have to stick to that for a n bit shift register. For an n bit shift register, we can use n flip flops only. Okay. So for a n bit shifter we can use n flip flops only, and that is very much clear to us that flip flop has a single input. It can accept a single input either as a fresh input or the output of the left flip flop or the right flip flop. But how all these things are to be covered in a single circuit? Because we have already seen that the PISO, in that we have to isolate the parallel in operation or serial out operation, and in the bidirectional we have to isolate the left right and right to left shifting. Okay. So in the case of universal shifter, we have to isolate all these 5 functionalities which are further left to right and right to left ones. Okay. So this is going to be a very complex task, and in addition to flip flop, this time a 2x1 multiplexer will not be sufficient. We will be using a 4x1 multiplexer instead, and instead of placing the multiplexers between the flip flops, we will be placing them separately in above the flip flops and with some different alignment of the flip flops and multiplexers. So let's cover that topic and the circuit. So this is clear to us that a 4x1 multiplexer is going to be used. So let's start with this. In this you can see that there are 4 D flip flops. This is D flip flop A, this is B, this is C, and this is D. So these are the 4 D flip flops. These are the 4 multiplexers. We can also name them as multiplexer A, multiplexer B, multiplexer C, and multiplexer D. Okay, this you can see that these are the 4 inputs on the lower side and there is a single output on the upper side of the multiplexer. Then one more thing which is very common, which we have used in all the flip-flops, that clock of all the flip-flops will be connected to a common point. So this connection we can prepare first of all. The first connection has to be this one. Okay, so these are, till now these are 4 D flip-flops connected in synchronous mode, and there are 4 isolated multiplexers. There is no connection being formed. So let's start with the basic operation. Okay, the simplest of the operation is the parallel in, parallel out. Okay, so for the simplest of the operation, parallel in, parallel out, we have to choose one of the inputs from this multiplexer's input side. Now let's choose that this third input. Okay, this third input be the parallel input. Okay, so let's choose this third input of the multiplexer, all the multiplexers actually, as the parallel inputs, and the select lines of all these multiplexers will be common as well. So these are my select lines. I am naming them as S1 and S0. Okay, so here I am preparing the operation table. So if S1 S0 is equal to 1 1. Okay, so if I am choosing S1 S0 is equal to 1 1, then you can see that if this is 1, this is 1, then third input of all the multiplexers will be selected, and third input of all the multiplexers are the separate parallel inputs. That means operation that can be performed by choosing S1 S0 will be parallel in. Okay, so parallel data can enter the multiplexer first, and the multiplexer's output will be connected to the flip-flop's input. Okay, so we just need to apply a clock here. Okay, we just need to apply a clock here. As soon as the clock is applied, this data which has entered from the multiplexer input to the multiplexer output to the flip-flops input will be available here as the parallel outputs. Okay, so to complete the PIPO operation, we just need to choose S1 S0 is equal to 1 1, and here my parallel data. Parallel output data can exit this shift register. Okay, so now let's cover another shift register case. Okay, so for that we have already done the parallel in part, so let's choose parallel in serial out. Okay, so for this serial out operation, now we have to choose between the serial out for left shift or serial out for right shift. Okay, so again we can choose for this 1 0. If I choose 1 0, that means 2. Okay, so for this 1 0, I will be shifting the data towards the, so if this is my data, I am changing the color. So I am choosing this second input of all the multiplexers for left to right shifting of data. So data is already available at the output in form of parallel outputs, but if it is a parallel in serial out shift register, then there will be only one output which will be accessible to the user. So that has to be the extreme rightmost in case of right shift. Okay. Similarly, this one, and this can be D out from right side, as there is a single output terminal. Okay. And similarly, if this would have been, so in for this 1 0 case, we can say that it will be serial out left to right. Okay. Similarly, this second terminal of this one can be used as D in for from left side in case I want to perform SISO operation. Okay. So if I want to perform the SISO operation, I can simply choose this 1 0 case. Okay. Then for this 0 1 case, now let's again change the color. For this 0 1 case, let's prepare another path for right to left shifting. So for right to left shifting, that means this output has to be connected to this 1 number input. Similarly, this one to this one. Similarly here, okay, and this one terminal can be used as D in from right side. So this can be labeled here. This will be my, this terminal will be my D in from right side. Okay, and in that case, this will be my D out from left. So for this, we have to make an arrangement. That means if I choose 0 1, I can perform serial out right to left. Okay. That means if I want to perform PIPO, then S1 S0 should be equal to 1 1. If I want to perform PISO, then S1 S0 has to be 1 1, and then 1 0 or 0 1, depending on whether you want to perform left to right or right to left. Similarly, for SISO, you have to SISO for left to right, you have to choose 1 0 and 0 1 for right to left. So all these operations are already covered. Now we have to cover one more operation, which is, or we can see that the one terminal of the multiplexer, 0 number terminal of the multiplexer, is still unused. That means we can add some more functionality to it. Okay, we have already seen that SISO is covered, PISO is covered, SIPO is covered, and SIPO, for SIPO we need not to do anything special. This same thing can be used for SIPO as well, which has been used for SISO, because in case of the only difference between SISO and SIPO is that the outputs will be available simultaneously. Okay, so we need not to do anything. The only thing is we just need to apply half the pulses, because after the end of 4 pulses data will be already out of the shift register in case of SIPO. And in case if I want to design SISO shift register, then I have to apply 8 clock pulses to take the data out as well. Okay, so all these four functionalities with right to left and left to right, all these functionalities are covered in this single circuit. Now the only thing which is left is the zero terminal of the multiplexer. Now this zero terminal of the multiplexer can also be put to use if I say connect this terminal to the output of this flip flop only. That means D flip flops output is connected to the D multiplexer zero terminal. Similarly, C flip flops output is connected to the zero terminal of this C multiplexer. Okay. Similarly, here as well, B output of the flip flop will be connected to the zero terminal of this D multiplexer. Similarly, this A output of the A flip flop will be connected to the zero terminal of A multiplexers. By doing this, we are simply connecting the output in a loop, in a closed loop with the same flip flop itself. As we can see that this output will be reaching the multiplexer's zero input, it will be connected to again back to this same flip flop only. That means the data will keep rotating in this D arrangement only, here C arrangement only, B arrangement, B, A arrangement. That means there will be four closed loops between A, B, C and D separately, and the data will keep rotating in that only. Okay, so this thing we can already also cover here as if we choose 0 0, then there will be, then this shift register will be locked. That means data cannot change. Okay, so with this we have covered all the four functionalities of the shift register: SISO, SIPO, PISO, PIPO, left to right, right to left shift, and one more additional thing, which is this locking of the shift register. So if we choose 0 0 on the select lines, then the output of that flip flop will be entering the input of the same flip flop via the multiplexer. That means it will not be changing its states, as the flip flop is already a D flip flop. It is not going to change. Whatever we will be applying at the input, the same thing will be available at the output. So in case of 0 0, my output is not going to change. Okay, so this is how we can design a a universal shift register which can be used to implement any of the four, or we can say four functionalities with left to right or right to left provision. Okay, so with this we come to the end of this lecture. Thank you very much.